Okay, it's now live.
Okay.
Should be good.
Probably not going
It is being live streamed actually. All right, everybody. Hello. Let's get started. We're here today for the PhD defense of Meredith Rawls. Meredith graduated from Harvey Mudd College in 2008. And she went to do a master's degree at San Diego State University, working on some binary stars like this. And then in 2010, she came to our program. She's worked on a few different projects, but the one she's going to talk about today has to do with red giant stars, asteroseismology, and eclipsing binaries. And she's going to tell us all about it. All yours.
Thank you very much. So I want to start off by acknowledging all the people who have helped me a lot, and I could spend half the talk just listing names, but I will spare you that. I would like to especially thank my committee. You're all in one room right now, and that's wonderful, so thank you for being here. And thank you also to Jean, who's sitting over here with knitting, who I worked with a lot on this project, and all of you for being a supportive community throughout the many years I've been in this program. So my thesis is about red giant stars that are in eclipsing binaries and how that is useful for asteroseismology. I encourage you, if you have questions during this presentation, feel free to raise your hand and ask. And then I'll also have a period for questions at the end. So, all right, so first off, just to give you a little bit of context, what is the point of this research and what am I kind of doing? This is kind of a big picture summary. So hopefully I don't have to convince you that measuring stellar properties is important and a thing worth doing, but just in case, stars make up most of the light in the universe. So if we don't really understand how that light, where that light comes from or what it's doing, we're not going to be able to understand much of anything else either. So that's kind of the super big picture motivation. And in particular, what I'm focusing on is eclipsing binary systems, so stars that orbit each other. And when you have a well-observed eclipsing binary, you can use that to directly measure the mass and radius of the component stars, which is really useful because the mass determines a star's fate, and there's no other way to directly measure those properties unless there's two things going around each other. Asteroseismology, on the other hand, is a newer technique that actually uses oscillations inside stars to measure their properties from the inside out. And it's powerful because you don't need the same dedicated set of observations as you do for eclipsing binary studies. And also, not very many stars are in eclipsing binaries. So while they're great tools, there's a lot more stars that have these oscillations, and you can characterize a large number of stars quickly using seismology. So what my project does is it takes stars that happen to be oscillating and are also in binaries and kind of studies them from two independent perspectives, which is unique because, as all the astronomers in the room know, you don't normally get an opportunity to observe something in two different ways. You know, we kind of are at the whim of what the light tells us, and this is kind of a cool opportunity. So taken together, a set of well-characterized binaries will let us explore the physics that's going on inside the stars that are in the binary, and in particular, a question that I'm focusing on is why not all of the stars have the oscillations that we think they should. So a little context for asteroseismology. Some time ago, there were a handful of stars we knew that had this oscillation behavior going on. And this is a graph showing kind of this population of stars as a function of temperature and surface gravity detected from ground-based surveys. So those are the black points, only a few of them there. And the French Corot satellite added several more, especially in this area of the plot, which is evolved stars, red giants. So this started to open up this new opportunity of seeing, of studying stars by their oscillations. When the Kepler satellite was launched, however, it really opened the door a lot wider. So now there are a whole bunch of these systems that we can study with their oscillations. Again, up here are the evolved red giant stars, down here are the main sequence stars like our sun. And Kepler, of course, was designed to find planets. You all know about Kepler. It's like the best spacecraft ever, but it's also really useful for stars. So, okay, what are these oscillations I keep kind of talking about in general? So the specific kind of oscillations that the stars I study potentially have are called solar-like oscillations because the sun has them. What basically happens is there's not like a driving pulsation mechanism like you get in other kinds of stars, but instead in the outer convection layer, the star is actually resonating. It's kind of ringing like a bell. It's stochastically driven, so it's not a, there's no other mechanism getting it to continue. And what's kind of neat is that the property of the oscillations varies as a function of the different kind of star you have. So a star like our sun will oscillate relatively quickly because it's a smaller star, but a big evolved giant star will oscillate a lot more slowly with periods of hours to days. And this lets us take observations that are spaced out more, have a longer cadence, and still see the oscillation behavior, which is really handy. And this plot is just to kind of illustrate how lots of things in nature have natural resonances, including musical instruments, but stars do as well, which is pretty cool. So how did it work? Here's an example of an oscillation spectrum of a star with solar-like oscillations. You can see that there's these different spikes in this power spectral diagram, and each of these spikes is an oscillation mode. You can immediately read two different properties off of a graph like this. You can read the spacing between modes of consecutive order, and you can read kind of the frequency of maximum oscillation power. So if you kind of fit this with a Gaussian and look at where's the middle of this oscillation distribution. So what these two quantities can immediately tell us is something about the star's surface gravity and something about the star's density. So immediately, just by looking at a graph like this, which you can get from a star's light curve from Kepler, you can kind of start to learn something about the star's global properties. This is a diagram here showing different kinds of acoustic pressure modes. Those are the kinds of oscillations that I'm going to be focusing on today. Solar-like oscillations can have two different forms. There's two different ways to solve the equations of motion in this situation, and some of them are pressure modes, where pressure is the restoring force. It's an acoustic, it's kind of like a sound wave. And the other is a gravity mode, where it's buoyancy is the restoring force, or gravity. Those are not really going to make much of an appearance in the talk today, but I can tell you more about them later if you're curious. So here's some examples of what a whole bunch of different stars' oscillation frequencies look like. This figure is from this paper here, and it's kind of cool because the smaller stars, their oscillation cone pattern is spaced out more, and it also is at a higher frequency overall. As the star gets bigger, more evolved, less dense, the oscillations get tighter together and go to lower frequency. So this, on the left side, the x-axis range has been zoomed in so that you can continue to see the oscillation pattern as the star gets bigger and more evolved. So this is something that a lot of stars do, that we have a lot of observations of, and this kind of gives you an overview of how it works. All right, so the first step, kind of as this project was being conceived, was to first we need to find red giants that are in eclipsing binary systems if we're going to study them from two perspectives like this. So working with Patrick led this project, and we found, we compared the red giants observed by Kepler with the eclipsing binaries observed by Kepler, and we just looked at them and see if there were any overlaps. Now, there were lots of false positives, and there's a lot of work to kind of eliminate those, but at the end of the day, we found 19 actual red giant systems in eclipsing binaries. Most of these are what we call SV2, which is a spectroscopic binary with signals from two stars when you look at the radial velocity curves. And but a few of them only have the signal from the red giant star, meaning that the companion star is very faint, and you can't actually see its signal when you look at the spectra. And I'll talk more about that later. And most interestingly, in my opinion, most of these 19 systems have a red giant that does have solar-like oscillations in it, but 4 don't. So that's kind of something we want to look at. On the right here, I'm showing a bunch of different light curves of these stars that Kepler observed. So this is a full 4-year time span, and the stars have these phone number names that mean a lot to me, but probably not a lot to you. And the ones that don't have solar-like oscillations are in red. So the ones with the shortest orbital periods are at the bottom of this plot, and the ones with the longest orbital periods are at the top. So one of these, right, this is one of the eclipses, and that's the other eclipse, and it just goes again and again. So you can see the shorter period ones more frequently. And then you get some really interesting cases down here where it's it's varying, not due to eclipses, but due to the actual star being magnetically active. I'll talk more about that later too. So that's kind of what we had to start with. So what does it look like when you actually characterize a star using this technique, this asteroseismology technique. This is an example of a double red giant binary that my paper came out on early this year. And in order to actually get a nice oscillation spectrum like this for this star, you have to process the light curves so that there's no gaps, and so that the eclipses are not there anymore. Because if you're taking a Fourier transform and there's a whole bunch of eclipses, you're going to get weird effects that you don't want, because it's not showing you the oscillation information, it's showing you other stuff in the data. So, and what we found in this star is that even though there's two red giants that are very similar, there's actually only one main set of oscillations. So there's these stars that are nearly twins, but only one of them is oscillating, and that's kind of weird. And in addition, the oscillation modes are broader and more damped than we would expect. So this graph here is showing upside down on the top is kind of a normal star with otherwise very similar physical properties. It's upside down, so you can kind of line up the frequencies if you want. And you can see that these modes are a lot narrower, stronger, kind of more typical thing you'd expect to see. Whereas our star, they're a lot broader and shorter. So something is acting to damp the modes and make them less strong than we would expect. In addition, both of the stars in this binary are evolved past the red giant branch onto the red clump, which may mean something about the oscillation behavior. Talk more about that later. So this is just to kind of give you an idea of how this looks. In tandem with this, we can study stars from the binary perspective. So this is now, we're using the Kepler light curve again for the binary stars modeling, but instead of processing it to get rid of the eclipses and make sure everything is nicely sampled, we are actually preserving the eclipses and not really caring about the stuff that's happening in between the eclipses. Because the eclipses contain information about, when one star passes in front of the other, you get information about the size of each star and all this different stuff. And so that's the priority in this case. In addition, you need radial velocity information. You need to know how the stars are moving in addition to how bright they are. And what I'm showing on this plot here is an example of how you measure radial velocities given a whole bunch of spectral observations of a binary star. So each panel is a single spectrum. Most of them are from ARCIS, the Apache Point Observatory's Echelle spectrograph, which is awesome. Some of them are from another Echelle spectrograph in Arizona, and two that are not shown are actually from Apogee, the near infrared spectra. So altogether, there's 20 some odd spectra for this system, and each peak represents one star's velocity at that moment. So the x-axis here is velocity. So you can see the stars are kind of, the velocities are moving in tandem as the two stars orbit each other. And from this, you can build a radial velocity curve and combine that with the information from the light curve to do a binary model. It's important, I learned, when you are combining velocities from different sources, it's really important for them to be on the same 0 point. So we all have to agree what zero velocity is, and that was super fun. So if you have questions about that, I can tell you about that later as well. As part of my project, I put together a suite of programs in Python that are available on my GitHub to help, basically to help extract velocities using this technique. It's actually an undergrad working with Jason now, so I'm helping to get this program up and running. So hopefully this can be helpful for people in the future who do things like this. All right, so once we have the radial velocities from the spectra, we get a radial velocity curve that looks like this. So one of the stars is moving towards and away from us, and the other one's moving kind of in the opposite sense because they're orbiting around each other. So that's good. And this is what the eclipses look like for this system. So over the entire orbital period, this is what it looks like when you zoom in on the shallower secondary eclipse and the deeper primary eclipse. They have this kind of rounded shape. Now, maybe you've seen other eclipsing systems and you know that they often have a flat bottom when one star is entirely in front of the other. Well, these stars are very similar in size, so they never actually get that flat bottom, and that leads to a few degeneracies in the fitting that were super fun. But what's interesting is that normally when you have something like this, you would think that one of the stars is bigger than the other one, because one of the eclipses is deeper than the other eclipse. But it turns out that actually the eclipse depth difference is due primarily to the geometry of the system. The orientation of the orbit from our line of sight and also the eccentricity of the orbit kind of combine to make this strange eclipse depth difference. So that was fun too. And in order to get this fit, which is the black line, I'm using a program called Eclipsing Light Curve, or ELC, which simultaneously optimizes 16-bit parameters and processes both the light curves and the radial velocities together to minimize a chi-square function. It uses a differential evolution MCMC optimizer technique to do this, and it's really awesome. So if you have questions about more details of that program, I'd be happy to answer that later as well. All right, so for this double red giant system, we initially thought that it was a big star with oscillations and a smaller star without oscillations, because, you know, okay, that's probably what most of the stars are like in our sample. But then it turned out that no, it was just the geometry confusing us, and actually it was two stars of very similar size. And we're pretty sure that the oscillations are coming from the one that's slightly smaller. The two stars are so similar in their physical properties, their mass, their radius, that we're not completely 100% able to say, yes, this is the oscillating star, because the asteroseismic mass and radius agrees with both of these values that we get from the light curve and radial velocity modeling. So, you know, we're pretty sure that it's a star for reasons I'll explain in a bit, but it was definitely interesting to say, oh, this is not what we thought it was. In addition, we think there might be a small set of oscillations coming from the other star. It was a very tentative detection, and it's difficult to say for sure because the modes are so broad and so damped. So there could be a second set kind of hiding in there. It's uncertain. But what's interesting is that when you take the eclipses out of the light curve, just like get the eclipses out, and you look at just the variability of the binaries brightness, like independent of eclipses, it's actually pretty variable. So this is in percentage, and overall there's as much as 2% variability peak to peak in this star. So it is slightly active. There's some star spots and stuff causing the brightness to vary, not because of the eclipses, which we think is probably what's causing this star to have basically no oscillations and this star to have damped oscillations. So that was kind of how we were able to piece together the story for this star. Of course, this isn't the only star that I'm going to talk about for an entire hour. There are a bunch of other systems. There were 4 that didn't oscillate, that were other red giant eclipsing binary systems. They all have main sequence star companions. They don't. This is the only one that is two evolved stars together. So in this case, when we look at the different oscillation spectra, we look at them really carefully. We don't see oscillations. So here's a set of oscillations in one star that's in one place, and then kind of the, you know, a different frequency, but still very clearly oscillations. We look at the other ones, we don't see any of that oscillation behavior going on. So all of the modes are affected equally in this case. There's not like, it's not just preferentially damping with the L=1 modes like another paper recently discussed. It's damping all the modes equally. And in some cases they're damped, but in some cases they're completely gone. This is a completely gone situation. So the opportunity here is that because we have the binary modeling at our disposal, we can characterize the stars that do oscillate and don't oscillate in very good detail, and then compare their physical properties to see what's different about them. All right, so another tool that I mentioned, we used spectra to get the radial velocities. And spectra are great for velocities, but they're also good for other things. So this is an example for the double red giant binary again, where we're using a Fourier decomposition technique to actually put together all the different spectra that we have observations of over time, and we put them together in a way that we get one spectrum for each star out of the end. And this is really helpful because when you look at any individual spectrum, you're going to see a signal from both stars together. Especially in this case, when the brightness of the stars is almost equal, you're getting just about a similar amount of signal from both of them, and it's all together, and sometimes the lines look sideways because one star is moving and one star is moving the other way. So for example, the H-alpha profile here is kind of a little lopsided and has a weird little side thing on it. That's the other star's H-alpha profile. But then when you separate them out, you can see in the zoomed panel that there's a single line for each line where there were previously double lines in all the observed spectra. So this is a really cool technique, and I also wrote some Python programs that that help people run this tool to do something like this. And once we have the spectra, we can use them for two main things. We do stellar atmosphere modeling to pull out effective temperature, surface gravity, metallicity, and we also take a close look at some of the individual absorption features that may be sensitive to magnetic activity to see if we can quantify that in a way that's not just the photometric variability that we saw earlier. And in this particular case, the stars have very similar temperatures. They're both about 5,000 Kelvin. All right, so when we take a look at a few regions in the spectra that might tell us about magnetic activity, we see something kind of interesting. So this is again the double red giant as an example. So we looked at a handful of these iron 1 lines that were potentially sensitive to magnetic activity and some that weren't, and just took a look to see if there was any apparent difference between them. And we actually looked at, I think, 3 of each, 3 that were sensitive compared to 3 that weren't sensitive, and they all look the same. So that wasn't very useful. So I only have 2 of those up here. And the line is a really faint dotted line showing you the individual line that's being considered in each of these panels. So in this panel, in the calcium panel, it's actually 2 lines that we're looking at. And in all the other panels, there's just a single line kind of in the middle that we're looking at. So what I would have liked to do is look at the calcium H and K lines, which are out in the blue and are very well-used, common, friendly lines that you can use to take a look and see if there's emission that is indicative of chromospheric activity. But because these are red giants and the continuum out there is a mess and the signal noise is very low in the blue on Ursus or Arcus, it's just not really possible, unfortunately. So what we do instead is we take a look at the calcium 2 lines that are out in the 8,000s, where a lot of signal, and the spectrograph goes out there. And we look for if there's any sign of net emission in the core of these lines. And there's not. You know, it was like maybe there would be a little bit, but there's not in this case. But one interesting thing we did find, we took a look at the H-alpha profile, and we found that for star 1, that it was significantly deeper than the model predicted. And for star 2, it was like a little deeper than the model predicted, but not a lot. I'll come back to talk more about this later, but in the paper we wrote that this may be indicating like a low level of chromospheric activity, and we use this to support the overall photometric variability of the star to say that it's probably star 2, which has been plotted in yellow this whole time, that's having the oscillations, because it has it's less different. So this star might be more magnetically active and have more suppressed oscillations. So we assign the oscillations to the yellow star at star 2. But again, that's not a for sure thing. So, however, it is important when you're using this technique, you need to have an orbital solution for your binary. You need to know how the radial velocity curve is for the entire orbit, and you also need to know the light ratio of your 2 stars. So this case was pretty straightforward because the stars are almost identical, so we could get away with saying, okay, the light ratio is 1. Let's move on with our lives. That's easy. But the other systems is not so easy because the main sequence companion only makes up about 5% of the light. So that can make it a little more fun. So in order to get a better handle on the light ratio and also the temperatures of the stars, one technique that we looked at was getting observations with the 1-meter telescope at Apache Point Observatory, just photometry in different color filters. And the idea of the motivation behind this was to get an idea of how the eclipse depths differ in different band passes. Because one drawback of Kepler is that unfortunately it only looks in white light. It has a broad band pass. It seems kind of like what you and I see, only it's like black and white, so a single color. Whereas by using the BVRI filter combination available at this telescope, you can get a different picture of how different parts of the star's light output vary during the eclipses and not during the eclipses. So the results here were kind of mixed. I've put 6 stars up here, and I've plotted in gray, kind of faintly in the background, what the Kepler light curve looks like when you fold it over one orbital period. And then all the different colors represent B, V, R, and I, respectively, for the 4 different filters. So unfortunately, this star is so variable that this doesn't really help us very much. You can see the variability continues, however, so that's kind of fun. Unfortunately, this star, the eclipses are so shallow that the scatter in the BVRI light curve is too big to really do much of anything. However, the good cases are that in this system, we were able to get some points during the eclipse and some points immediately before the eclipse, and feed that into our light curve model and get a slightly better solution. And the same for this star. We were able to feed in, there's a couple points during eclipse and a couple points out of eclipse. And you can see that the eclipse is deeper in blue than it is in red, which is telling you about the relative temperatures of the stars. We could have potentially done the same for this system and this system, but we don't do it for this system because there's some phase effects in the light curve that complicate things a little bit. And there were only like 2 data points for this star, so we didn't bother to add those because its solution was already very robust. It probably wouldn't have made much of a difference. So I would like to continue this kind of observation campaign to maybe build up a bigger sample of stars in the future, but this was still very helpful for a couple of the systems where the companion star was super faint. It was able to really help us constrain this. So that was handy. All right, so I've been talking a little bit generically about, there's this one double red giant binary that I had a paper on, and there's these other systems in our sample. I told there was 19 of them total. Well, in my work, I'm focusing on 7 of the other ones. And I chose these 7 additional stars based on, so that they were representative of the entire sample of 19 stars, and I figured closer to these ones. So I picked, there's 2 stars that don't oscillate at all. There's a large range of orbital periods, everything from about 20 days to over 200 days, so getting a nice coverage there. 3 of them are variable more than 1%. We saw earlier the one star is variable at the 2% level. 2 of the systems have a little bit of phase effect. So what I mean by that is that the light curve varies consistently each orbit in a way that's not related to the eclipse. There's a mix of eccentricities from nearly circular to like over 0.3. And these were also the stars, some of the stars that were observed the most just by chance and timing in our 1 meter photometry campaign. So all these factors combined, these are the light curves of the stars that we're looking at. I think it's actually 8 here because this one is the double red giant that I already talked about. So these are the light curves, the Kepler light curves of those stars. All right, so here's kind of a snapshot of the analysis techniques I've already mentioned, and kind of what it looks like for a few of these different stars, like the process of getting the useful numbers out of them. So on the left, I'm showing an example of the broadening function technique to get the radial velocities out for a system where there's a main sequence companion that's relatively faint. So before, when I showed you this for the double red giant binary, there was like 2 very obvious peaks in each of these panels, and it was great and easy, and I could fit 2 Gaussians, and life was wonderful. In this case, there's like 1 obvious peak, and then there's maybe like a little blip here and there. So that is super great. Gina and I both know how super great that is. And so it can be a little challenging, right? Because this blip is real, but here there's like 2 blips. So which one's the noise blip and which one's the star blip? So that's great. But at the end of the day, you're able to use, okay, if this star's here in its orbit, this star shouldn't be like here in its orbit, it should be here in its orbit. You can kind of piece together where the velocity peaks more or less should be and figure out which ones are real and then measure them, which can position very precisely. So and this was done for all the stars. The disentangling of the spectra that I showed you before, I was able to get good spectra out for both the stars, again, because they had equal brightness. But now the contribution from the second star is only about 5% of the light. So we're only able to get a good disentangled spectrum for the red giant component, the main component. So it's basically taking 15 to 25 of these input observations where there's light from both of the stars, and it's again using the same Fourier decomposition technique to get out in the end the red spectrum, which is the giant spectrum. You'll notice there's a little bit of waviness in the continuum from time to time. That is an unfortunate artifact of this technique, just because whenever you do anything with Fourier transforms and sine curves, they assume there's no end, and that's not how reality works. So that is one of the unfortunate side effects of this technique that can make it a little challenging when you're trying to do precise stellar atmosphere modeling. Finally, on the right here, I'm showing you the result of one of the ELC fits. ELC is the program that combines the light curves and the radial velocities to make the physical model of the binary. And so it is simultaneously optimizing 16 different bit parameters. So each panel here is one of those bit parameters. So most of these are very well sampled and nice distributions, and you can read off, the middle, and you can get an error bar out of that, and life's wonderful. Those are a couple exceptions. So here is the temperature, and like I said before, the Kepler bandpass is a white light bandpass, so you're not going to be able to constrain temperature hardly at all. So we basically just throw away the temperatures that ELC fits because we can get spectroscopic temperatures that are a lot more precise. And another exception to the lovely distribution rule is this contamination factor. So in this particular system, there's a really bright star nearby, and sometimes, depending on the aperture that was chosen for that star, there was some contaminating flux from the nearby star that kind of drove up the other light contamination a bit. So ELC wasn't really sure if that should be above 5% or not. I told it it's probably not more than 5% after taking a look at it, and it just thought maybe it was, but it's wrong. So probably wrong. So that's why that distribution looks a little bit askew. But altogether, these this varies with the orbital period and the relative radii of each star and amplitude of the radial velocity curve and limb darkening coefficients and eccentricities and inclination and all this stuff is fit together with the data from both the light curve and the radial velocities. So that's what that looks like. And again, this is done for all the systems. One of the systems is a binary that's only single line, an SB1 binary. And so in that case, we still fit all of the same parameters, just a few of them basically come out like flat distributions because they're not at all constrained. If you don't have your second radial velocity curve, you're not going to get the mass for that star, for example. So in this case, we had radial velocities for both stars, so everything is pretty well constrained. But for that one exception, we only got like relative radii. We didn't get absolute masses. All right, so now I'm going to go through each of the 7 systems and kind of give you a brief introduction to them and tell you their main highlights. So I'm going from shortest period to longest period. This is the one with only one radial velocity curve. You can see it over here. It has a lovely fit through it, but it doesn't have another radial velocity curve because the companion star is a tiny little M dwarf. So that's not going to happen. So, okay, I just told you I couldn't get masses, but there's masses up here. Those are from Asteroseismology. I cheated and assumed those were right. One thing we're trying to do is test and see if they're right, and in this case, you can't use this star for that. But if you combine the binary modeling with a single radial velocity curve with the information from seismology, you can estimate what both components, masses, and radii are. So I've done that here. This system has an eccentricity of about 0.1. It has some variability. You can see the full light curve down here. It's not like highly variable, but there's some wiggly stuff going on. And when we take a look at the magnetically sensitive regions of the spectra, we don't see anything interesting in calcium at all. It's very much like the model predicts. And each of these models was chosen so that it's close to the actual star's parameters, if you want to know more about that. And however, the hydrogen alpha profile is deeper, kind of like we've seen previously. So that's potentially interesting. We'll come back to what that might mean once I get through all of them. Next up is a star that does not have solar-like oscillations. So this also has a pretty short period. It's about 20 days. And the eccentricity is basically 0. It is pretty highly variable. So all of this, the spiky dips in the light curve are the eclipses, but like the overall kind of sinusoidal business going on, that's actual variability on the star itself. So you can see in the eclipses, there's a lot of scatter going on. Even though the fit goes through the middle of it, there's a lot of variability that's just due to the fact that there's spots on the star and they're rotating in and out of our view and making kind of a mess. So what's cool about this one is that it has pretty clear net emission in these calcium-2 lines. Right? The profiles are a lot shallower than the model predicts. So that's telling us that that there's definitely magnetic activity on this giant star. The H alpha line, on the other hand, is pretty normal. This star is one of the fainter ones in the samples. The spectra are the noisiest, unfortunately. But we're able to get the masses and the radii for each component out.
Can I ask a question?
Sure.
So you only see that variability in the eclipse, which is a bit strange, but is that because you flattened the light curve?
Excellent question. Yeah, so you're only seeing the variability in the eclipse regions here because we've taken the variability out for the light curve modeling between the eclipses. Yeah, that's exactly right. It's not really useful when you're modeling just when one star goes in front of the other. So we flatten that out of eclipse variability to just get the eclipse profiles isolated. And the same thing is true here. In this case, we actually only use the region around the eclipse to fit it because there's not any information that we're using in the other part of it. This star is very similar. It has about a 34-day orbital period, also nearly circular, also no oscillations. So, this one and the previous one are very similar. And it has also significant calcium emission happening here in both the lines. And you can see that it has like big sinusoidal stuff going on. And the eclipses are actually these little blips that like occur in the middle of the activity. So it's like doing all kinds of stuff. And the H-alpha profile is like, it's not deeper than it should be. It's a little funny looking, but it's not, it's not one of the super deep ones like we saw before. There's definitely some net calcium emission happening here. That's again telling us the star is definitely eminently active. All right. Go into longer orbital periods. We get to this one. This one has a period of just about 120 days. So it's getting towards the longer period systems, but not as long as the 200 some odd ones. Its light curve has this interesting phase effect going on that occurs consistently with the orbit. So that's telling us that there's either a tidal effect going on where the star is changing shape a little bit, or there's a reflection going on consistently every time you have an orbit, something like that is happening there. You can see there's a lot of again, this wiggly variability going on in both of the eclipse profiles. It's showing us a little bit of stellar activity, but nowhere near as much as on the previous two stars. So it's only about at the 0.4% level. There's no apparent calcium emission in those profiles. And the H-alpha line is back to being super deep. So, all right. The next one, goal 578, it has an orbital period of nearly 200 days and is the most eccentric system of the subset at 0.38. It does not have very much variability. You can see that looking at the Kepler light curve over the full orbit. It's kind of just doing its thing. They're pretty far apart. They're orbiting. Not a lot happening there. The calcium does not show any strange emission, and the hydrogen alpha is, again, deeper than we would expect for this star. 703 is another long period one, over 200 days now. It's moderately eccentric, and it's actually very similar to the previous one. There's not a lot of activity going on. The calcium lines are normal, and the H-alpha is too deep. This is the one with the H-alpha that is the most too deep. An interesting fun fact about this star is that a good 25 of the radial velocity points plotted here actually come from apogee. The star happened to fall on like more than one field of view for apogee, and so we got a whole bunch of radial velocities. Apogee. Gina's working on a paper that features this star, and it's wonderful. And the last but not least is 997 with an orbital period of over 230 days. Moderate eccentricity, not variable at all. Its calcium lines look pretty normal, and its H-alpha, again, is deep but not like super deep. It has these gaps in the light curve, and that's just an artifact due to the fact that Kepler every quarter would rotate 90 degrees in the sky, and once every 4 quarters it fell on a part of the thing that was broken. So we don't have a completely discontinuous light curve for it, but there's still enough information here, several eclipses, and enough of a time span to pull out the oscillation information, so it didn't really affect the analysis. It's just kind of interesting. All right, so that's the cast of characters in this thesis. So to take this all together, we can test the asteroseismic scaling relations. So earlier on, I mentioned that you can read that delta nu and that nu max off the graph of the actual oscillation modes, and you can use that to infer the star's average density and surface gravity given a temperature. So down here, we're comparing the stars with what we get with the ELC binary modeling. We're comparing the density from that versus seismology. So in all cases, the ELC is the x-axis, and the seismology is the y-axis. We're comparing the gravity here. So again, the ELC this way, and the seismology that way. And there's only five dots on each of these plots because there's only 5 of these 8 total systems that have solar-like oscillations and that are sp2, that have a radial velocity curve for both stars. So that's how we get 5 points. Overall, the densities and the gravities match kind of okay, like nothing super off and wrong and terrible, which is why it was interesting to find that the actual masses and radii of these stars do not agree very well. So you can see that the asteroseismic mass for these stars is overestimated in 3 of the cases for sure, and the radius is overestimated in 4 of the cases. And there's error bars in these plots. This isn't just, oh, maybe it's the mirror that is really being overestimated by the scaling relations. And so what we're finding is that while the densities and gravities are nearly agreeing, the masses and radii aren't. And that the stars that are least like the sun seem to be disagreeing the most. What I mean by that is that generally, so you have the lower the density, the least like the sun, and the lower the surface gravity, the least like the sun. And the bigger the radius, the least like the sun, and the masses are actually about the same. But we think that the stars, it's a little hard to tell for sure with 5 data points, but it seems like, and this is also found using interferometry to compare radii, there's just a lot of scatter when you compare an interferometric radii with asteroseismic radii. But we're finding a consistent overestimate of these radius points. There's going to be some plots with more points coming soon in a paper led by Patrick, but they're finding the same basic result even with more of these points. So this is kind of one of the main results from this work. All right, so going back to the magnetic activity bit for just a little bit, kind of summarizing what all these stars were telling us together, we found that there's 2 of these stars that lack solar-like oscillations, and they also are the most magnetically active. They have short orbital periods, and the orbit has been circularized and rotates synchronously. We can tell that because there's the period of the variability is basically equal to the period of the orbit. That's a little bit off because of differential rotation, but it's basically 1-to-1. And the calcium-2 emission is also agreeing with the stars that are the most strongly photometrically variable, which is nice. It's probably a real tracer path. The H-alpha line is a little trickier to interpret because it is formed throughout the star's atmosphere. Some of it comes from the photosphere, a lot of it comes from the chromosphere. It's a little tricky to kind of nail down exactly how it's going to vary from case to case. One example I did find is a study in 1990 that compared a couple of different main sequence stars, where some of them showed calcium H and K emission correlating with deeper H-alpha absorption. And so since we're not able to use the H and K lines in this case, H-alpha may be a proxy, but it's probably not a 1-to-1 proxy. So all this is showing is that the stars, there was a real difference where the H-alpha line was deeper for these main sequence stars in this study for a couple of different temperatures of stars, and that did indeed correlate with calcium H and K emission. So there may be something there, but it's not as clear a tracer as the calcium-2 lines out of the 8000s that we use. All right, so I've been hinting a little bit at this idea of not just magnetic activity, but also a resonance between the orbit and the rotation of these stars, and using that to kind of look at tidal effects in addition to just, are there star spots? So this is a plot that Patrick has put together, and it shows a whole bunch of these different red giant interesting binaries. And in particular, it has a bunch of them on this 1-to-1 line. And what this is telling us is that the stars on this 1-to-1 line, they are rotating at the same speed they're orbiting. And all of the stars on this graph that are white circles have no oscillations. So there's obviously a correlation going on here where the stars that are kind of locked and resonant and highly variable, these bigger circles are more variable, are all tending to be the ones that don't oscillate or oscillate with lower oscillation power. So the things that I'm finding are consistent with the big picture, but my study is unique because it's able to actually probe each individual star in a more detailed way than this overview. But it's good that it's kind of consistent with this overview. And so we're finding that the tidal synchronization seems to be linked with the stellar activity. They're not just independent either or things that tend to happen together or not at all. Yeah. All right, so here's an example of how we can actually use stellar evolution modeling in order to constrain how the star's tidal forces have acted over time. And we can use that to kind of predict what the star should look like today. So this is going back to the double red giant binary. And we used the MESA stellar evolution code program. And what it does is it makes a one-dimensional stellar profile throughout the interior of the star for a whole bunch of different physical parameters. And it evolves that stellar profile with time. All you have to feed it, well, I mean, you can tweak a lot of things, but all you have to feed it is the mass of the star and the metallicity of the star. We have the masses from the binary modeling, and in many cases from the seismology, but we use the binary modeling masses. And we have the metallicity from the spectra from stellar atmosphere modeling. And so we feed that into MESA, and we let it evolve the star, just pretending it's a single star, the evolved one, until it gets to its current radius. So in this case, we ran a pair of models since both the stars are evolved in this funny double system. And we found that in this case, there were two potential solutions that agreed with the present day radius. So I know there's like a lot of lines in this plot, but what's happening is that the white lines correspond to the star that we think is oscillating. It could, hypothetically, be in the red giant branch part of its evolution and still have its current mass and current radius. Or it could be in the evolved horizontal branch red clump area of evolution, which is consistent with what the asteroseismology is telling us. Because you can actually use the period spacing of mixed gravity modes with the pressure modes to determine what the evolutionary state of evolved stars are, which is really cool and not what I did, but useful for comparison. And it very much is telling us that it should be up here. So we adopt these answers for each star's present age, because this maps directly to an age. These are error bars, dash lines, given its present radius, assuming a mass and metallicity. So this is really handy, and we can do this for the other stars too, and we do. One thing to note is that for this particular case, we had to adjust the mixing length parameter for which basically controls a scale length of what the convection acts over. So we had to make that length longer and essentially make convection more efficient in order to get the stars to be sufficiently small and still be in this red clump phase. The mixing length is just a way to parameterize convection. We don't have a full physical model of how convection operates, so there's no set number that parameter should be. But we found that if we bumped it up a bit, that we were able to get very good consistent answers, which is interesting. Taking a look at how the stellar radii evolved with time, you get this top plot. Okay, so what you're getting here is remember how there were two lines on the previous plot, right? It could have been a red giant star or it could have been a red clump star. That's what you're seeing here. This is a radius cut. And so it could be down here, we lumped these together and called it the same, or it could be up here. And in this case, it's up there. So, so what I'm showing down here is a way of measuring the tidal forces in the star over time. So I mentioned a minute ago that you can use stellar evolution model to predict how the tides evolve over the course of the star's life. You have to take into account a couple of things. You have to use how the star evolves, so how its size grows, how its temperature changes, how the amount of stuff that's convecting changes. All of that's handled by MESA. But in addition to that, you have to know about the companion star that's pulling on it, that's actually making tides be a thing. And so you need to know the orbital period and the mass ratio as well. And based on that, you can predict how the eccentricity should change over the star's lifetime, which is what we do for all the systems. So another case, this is the double red giant. It's two plots that I'm showing here. This is the part of the tidal evolution force that is only dependent on the evolution of one star and not dependent. I haven't added in the orbital period business yet. And it looks similar, it actually looks different for the star that's not nearly as evolved as the double red giant star. So this part of this graph here, that's the luminosity bump there, is actually the same part. It's like this part only. So the star has not evolved nearly as far in all the other cases. I'm just showing one representative one here. They all look similar. They're not identical, but they're all very similar. And you see that you draw the current present day radius, and you can use that to read off the current age of the star and you can compute the tidal force up to that current time period, which is what we do to compare them. So the result from that is shown here. The x-axis is showing it's a way of writing the expected change in eccentricity. So systems to the left of this dotted line are expected to have been around long enough for the orbit to circularize. Tides should have done stuff and kind of messed with the stars, and the orbits should be locked and synchronized. Locked and synchronized. If you're on the right of this line, then you have not yet had enough time for that to happen. The stars aren't close enough, and they haven't been around long enough for tidal forces to dominate, to change the eccentricity and pull all of them zero. So I've also color-coded these as a function of orbital period. So you can see that the ones with the shortest orbital periods tend to be the ones that are expected to be circularized, and the ones with longer orbital periods are not expected to be circularized. The y-axis here is showing what the actual eccentricity is. So, if it's expected to have, all of these points should theoretically be on the very bottom of that axis, and all of these points could kind of be wherever they want to be. This is the point 38, the most eccentric one. So you can kind of read a lot off this plot. You can stare at this plot for a long time if you want. I won't make you stare at it forever, but it's kind of suggestive because these two systems are the active ones, right? The active ones with no oscillations, with the most magnetic activity that are also have been tidally circularized. So that is again filling in this picture of, okay, there's some systems that have tides and magnetic activity that are damping its oscillations. This one is the one with the very low mass companion. So it's kind of like this funny outlier in between case that's not quite like, we think it should maybe be circularized, but it's not. It still has a 0.1 eccentricity. So it's kind of being odd. This one is the in-between case. It's the one with the 100-day orbital period. And it's like right on the cusp of maybe should circularize, maybe shouldn't. Which is interesting because of the long period systems, it has the most variability. It has about, I think it's 0.6% variability, or sorry, 0.4% variability in its light curve. It doesn't have any calcium emission though. So it's like an interesting kind of in-between situation. Whereas these three here are all pretty much behaving as expected, not a lot of activity, not a lot of tidal forces, and this is the weirdo double red giant. It's actually being pretty consistent. It hasn't circularized and it shouldn't have, so that's nice. All right, so the main prediction that I make from all this is that there is a continuum of different kinds of systems with evolved giants and binaries. And so on the one side, you have these so-called heartbeat stars. None of them are in our sample. We did find one when we were looking for red giant binaries in the Kepler data set. And they actually have, like, the fact that they're so eccentric and the actual orbit is inducing pulsations in the star. It's a different mechanism than we see in any of these cases, but it's really cool. And it's kind of one extreme of tidal forces and messing up what you would otherwise expect a star to do. And then on the far other end, you have these stars that basically are oscillating how you'd expect them to if they didn't have a binary companion at all. Right? They're not very active. They're not being too much affected by tides. They're just kind of doing their thing. And then in the middle, you have these kind of interesting cases where the oscillations are damped, like in the double red giant, where they were broader and more damped than we expected. You have, this is the in-between case that was in the middle on the previous plot, this guy here. So you have this one that's, it's actually potentially a little bit damped. And so it's not quite behaving like its friends over here, but it's not quite over in the no oscillation camp either. And then you have the weirdo with the M-dwarf companion that doesn't behave at all. The oscillations are damped in this star, but it's not circularized. So it's kind of doing something. But the big picture that I'm predicting is that you'll kind of find a range of systems along this continuum. All right. To wrap up, I just wanted to zoom out a little bit. A lot of you guys maybe care more about the galaxy than the stars. So these stars are in the galaxy, believe it or not. So here's a couple plots I made of distances to these stars. They're all in the Kepler field, so they're all kind of pointing in one direction along a line of sight towards the galactic center. This is the sun. This is the center of the galaxy. It's a black hole. These are concentric 2 kiloparsec rings going out. And I had just a 3D thing that I could drag around. If you want to play with that, you can come find me. And this is a plot more like you might see in a paper where you would look at just the galactic radius, distance from the galactic center, and the height above the plane. One thing we looked for is there a metallicity gradient, like you might expect to see in different heights above the plane? And the answer is not really. We have 6 points or 7 points. So there's no real clear metallicity gradient as a function of galactic height. But this was still kind of useful to see like how these stars fit in the galaxy. And finally, we also compared some of the physical properties of these stars from different pipelines and surveys that have been done. So for example, the KIC, the Kepler Info Catalog, does its best to kind of guesstimate temperatures and gravities and metallicities and stuff for these stars. Doesn't always do a very good job, and it has really big error bars. It's the purple points. It's not like wildly guessing, but the errors are big and not that useful. The blue points are from the Apogee pipeline, data release 12, and you can see that it generally, for the most part, is agreeing for the temperatures, the metallicities, and kind of the surface gravities. Surface gravities are interesting because we find generally that the spectroscopically determined surface gravities that we get tend to be higher than both the dynamic binary surface gravities and the asteroseismic surface gravities, which is something that people have found before. This isn't like a new wild thing, but we only have, again, like 7 stars that we can really compare, so it's hard to say for sure if that's a real offset, but we think that is a thing that we're seeing that's consistent with what people have seen in other places. The Canon is a recent paper that came out that processed the Apogee data in a way that didn't use like stellar physics. It used like information pattern, machine learning stuff, and it got super precise measurements for a few of the stars, just the green points here, and you can see they mostly agree with the other points. MESA spits out what it thinks the star's properties should be when the model finishes evolving, and the fact that the orange points aren't off in their own land means the MESA models aren't totally wrong, so that's nice. And then the stars are the dynamic results of this work, and the red circles are from the stellar atmosphere modeling that we had to do to get the temperatures and stuff from the high resolution spectra that we have. So you can stare at this again for a long time and look at what's kind of not consistent and what kind of is consistent. But the main point is that these stars are good calibrators and reference points for survey data that are going to be spitting out a bunch of values. All right. So finally, to conclude, overall, I've found that solar-like oscillations tend to be dampened by magnetic fields and by tides, and that those effects usually occur in tandem. It's not usually just one or the other. It's usually they're both happening or they're not both happening. This is most pronounced for the systems that have short periods, and then obviously they're spotty because they're magnetically active, and they also are synchronized in their orbit and rotation. We find that asteroseismic scaling relations are not like completely wrong, but they're the least accurate for stars that are least like the sun, and they are consistently overestimating both mass and radius in these stars. These stars can be useful references for surveys in the future, and it's also important to keep in mind that future asteroseismic surveys are going to miss stars that are magnetically active and in close binaries. Thank you very much.
So I actually have a few questions. One about Fourier transforms, but I wanted to start with the iron lines.
Sure.
So I was just curious, what is it about, what's happening at the atomic level in an iron nucleus or an iron atom that causes the iron 1 transition to be magnetically sensitive?
So I don't think it's iron in particular. It's just that that some of those lines have like this was from a paper in like the 70s where they looked at like all the iron lines because they were measuring them anyway to get metallicity, and they noticed that some of them were more prone to like Zeeman effects or broadening in the presence of magnetic activities than others. I'm not sure about the detailed physics of what makes one line different from another. I mean, they're all iron 1, but they noticed just empirically at least that there were some that were more like that and some that were less like that.
But you use those iron lines as your primary tracer of magnetic activity?
No, well, it was one of the ones that we tried but didn't really find any results with. So we focused instead on the calcium lines and then potentially the hydrogen alpha.
Okay.
Yeah.
And okay, my next question about Fourier transforms now.
Okay.
So you mentioned something about artifacts due to to assuming an infinite Fourier transform. So does anyone in the field or anyone at all try to use wavelet transforms instead of Fourier transforms that would forego that infinite assumption?
That's a good question. Trying to use wavelets instead of Fourier transforms. I don't know if that's been tried for spectral disentangling, but I like that idea. I mean, this technique that I used was written up in a work around 2004. I think it was some guy's master's thesis. And so, I mean, the technique could potentially be adapted to use wavelets and maybe be a little less wiggly in the end. That's a good idea.
And one more really quick one. So there is a sentence that I saw where your slide said that most magnetically active giants are rotationally synchronized. So by rotationally synchronized, did you mean there that they weren't differentially rotated?
No, sorry. I meant when I said synchronized, I mean like tidally locked. So the orbital period and rotational period are locked together. Yeah, there is a little bit of differential rotation that we see when that's the case. The periods aren't exactly the same, but they're basically the same. Yeah. Good questions, thank you.
Gene.
Did you try to quantify the magnetic activity in any way with your lines, or did you just kind of look at the spectrum and this one's deeper? And what sort of quantifications of like magnetic activity are made, and could you make any of those comparisons?
Sure. So I took a difference, right? So I think you're specifically asking, like, did I measure exactly how different each model is from each line, and then like compare those like quantitatively on a graph or something?
Yes, that just seems like a good idea to do, to quantitatively describe it.
Fair. I mean, it seemed pretty clear in this case for the calcium lines, at least, that there were two where it was very much not matching the model, and the rest pretty much matched the model. That I didn't do it for this set of stars, but I think that if we're going to use this method for a bunch of stars, which we're planning to do, for all the systems, that would be a really good idea.
And then a corollary to that, H and K are present in the spectra. They are there. It's just that you have to pay particular attention and care to detail when doing it. But you can measure things like the calcium index, which is in the sun is a very common indicator of magnetic activity, and I think that's something that's worth measuring, and you could measure in these spectra.
Okay, no, that's a really good idea. Is maybe taking a closer look at the calcium H and K lines. I mean, you've done a lot of the spectral reductions, so you know a lot about what
I know
is
they're there,
possible?
and I know they're messy to work with,
Yeah.
so I'm not doing it.
Oh, great, thank you. What an awesome suggestion.
Gene Murphy. Did you have a question? Okay. Put that at the James.
So there were four things you plotted against each other, and two really worked and two
Yeah.
didn't. Mass was one of the ones that didn't work, as I recall.
There you
Yeah.
go.
Yeah, there, okay. Oh, there we go. So there's error bars in both dimensions, right?
Sorry, there.
I mean, both of these are measurements via some technique. So there's your error bars in the X and error bars in the Y.
Yes, there are.
right?
Yes.
So is there any case when the error bars don't overlap at all, in that the measurements from both things are completely, totally different? And in that case, then which one is wrong?
Well, I personally believe gravity. So that's actually a really good question, though. Just which one is wrong? We are showing there's definitely an offset, right? For example, this one's mass does not agree with the error bars for that star from the seismology and the binary modeling. I think that the binary modeling is more likely to be correct in this case, because we're seeing the asteroseismic scaling laws rely on, it's basically an empirical scaling, assuming that some properties can just scale up, right? And there's a couple of different approaches that you can use to get the final numbers out. We use, there's the asymptotic assumption is a thing you have to, a way that you correct the delta nu that you observe to be like the hypothetical delta nu that actually is measuring the star's density. And so there's a couple different ways you can approach that. And we tested that with the two different ways of plugging those numbers in, and we found that the asymptotic correction that we used here actually gives us more agreement than if we don't use the asymptotic correction. So I think it's telling us that we're on the right track when we do it that way, but that there really is a difference in the two values.
And are all these things orthogonal in that if the mass is off, the radius is also off, or are these all completely orthogonal from each other?
How do you mean?
Well, for instance, say I get one of my masses, so I'm telling you my radius is also going to be out.
Oh, I see what you're saying.
Or is it a case of like, I know everything else right, but I just have mass wrong?
Sure. No, you could have just a mass wrong. Yeah, I mean, so for the seismic scaling laws, right? You're combining both the nu max and the delta nu, because one gives you surface gravity, one gives you density, and you can combine those to get a mass and a radius, right? So it's difficult to nail down exactly which of the scaling laws isn't working in this case. So that's a potential issue. But for the binary modeling, if you could be wrong in mass or radius a lot more easily, then you're more likely to be wrong in both for seismology.
Ethan.
Because you're looking at binary systems, does tidal deformation influence your determinations of these in a significant way?
Sure, good question. So these are all very well separated binaries. Some of the radii never exceeds, I want to say, 5% of the separation. That might be wrong. I have the number written down in my thesis. But they're all well separated in that tidal effects are not going to be significantly distorting these stars like you might see in a closer binary system. That's a really good question. I think all of the red giant binaries that we've found in Kepler so far, I think, are well separated like that. So we haven't had to deal with the details of, if it's not a sphere.
Okay, so follow-up question. On the other plot where you showed that the stars that are not oscillating, they tended to be at shorter periods. Are the ones that have really short periods now, are those deformed enough that there's significant damping, and that's the reason why they're not oscillating?
Sorry, say.
Yeah, so if you have two short period stars, I presume they're orbiting much closer.
Yeah.
They are.
Yeah.
Uh,
I can tell you.
So does that have a significant effect on damping the oscillations because they would be more tidally deformed than the ones that are further separated?
Sure, quite likely. Yeah, it's unclear if the actual physical mechanism that's making the oscillations get damped is more a magnetic thing or more a tidal thing, but because they always seem to occur together, right?
Oh, okay.
So it could very easily be that the actual mechanism is the convection region is being like stretched asymmetrically in the closer stars, or it could be that there tends to be activity on these stars and there's a magnetic effect that's giving you the damped oscillations. It's not really clear which is the underlying.
Gotcha. Cool. Thank you.
Just kind of like a little thing on this, the gravity plot on this slide.
Yeah.
What are the gray points?
Good question. So there are a few gray points on this slide that I didn't draw attention to. These are the spectroscopic gravities. So near the end, I pointed out that we find that the surface gravities measured from both seismology and the binary modeling pretty much agree, but that generally when we get the surface gravities from spectroscopy, they tend to be systematically larger. They also have larger error bars, so there's a lot going on there. But we do find that for all of these systems, the log G is overestimated spectroscopically.
True. Are those from Apogee
No, Arcus.
Emma.
You talked about the orbits circularizing. Why does that happen?
Sure. So when you have, it's the same reason that kind of the same reason that the moon is tidally locked to the Earth and the base is the same way, right? So you get basically over time the tidal forces act to kind of tug on the two bodies, and given enough time and enough tidal force, they will eventually both first they'll lock up like that, and then after that the orbit will tend to become more circular. It's a good old special mechanics problem, but that's how it works.
Sam.
So you talked about the calcium 2 line as your indicator of magnetic activity, and then maybe increased H alpha absorption depth. But then the stars that you showed either had calcium lines or increased H alpha absorption depth.
Yeah.
So if H alpha is a proxy for magnetic activity, why are they never the same and only exclusive?
Excellent question. That's very true. When we see the calcium net emission, we don't tend to see the excess hydrogen absorption, and vice versa. When we see the hydrogen net absorption, we don't tend to see the calcium emission. So there's a couple potential answers to that discrepancy. These calcium lines may not be as sensitive as, for example, the H and K lines that Gene thinks we can maybe measure. And so maybe it's just not quite strong enough to get them to show the net emission. But then, shouldn't it show the hydrogen as well? And I don't know. It's a very good question, and it is notable that we see the excess hydrogen alpha absorption in the stars that don't appear to have the calcium emission. So that kind of calls into question whether it's that great of a measure at all. But it is consistent in all the long period systems. So it may just be like a lower level activity measure, but not enough of one that it messes it up, or it might just be not a very good metric for activity.
And can you go back to one of those slides where we see the spectra? Because
Just like one of the star.
sure. That'll work. So it looks like the H alpha difference is double peaked, and that was sort of consistent through all of the lines that you showed.
Oh,
Can
it
you-
doesn't line up quite.
No. So
exactly.
So go back to that previous one, right? It's got two dips in the H. So in the H alpha absorption difference, there are two minima,
Oh, yeah, that's what you're saying.
and that seemed pretty consistent through most of the lines. So why?
I see what you mean, and I'm not sure. It might just be a difference in the rotation, but they're not rotating very fast. I'm not sure. Extend on the answer?
I mean, it could be, how are you modeling that the H alpha lines are you using? Because I know Move has like a hell of a time and hydrogen lines.
Right, no, yeah, so hydrogen line models with LTE atmospheres are notoriously not necessarily great. Yeah, bad, that's the word. It's Tom's favorite. Yeah, so these are all from, it's a high-res, it's called high-res set of spectra that were in a paper from a few years ago. And I picked model spectra, they are LTE model spectra, and I picked ones that had temperature, gravity, and metallicity closest to each star. And the resolution was already about the same as Arcus, so I didn't mess with the resolution. And in the case of the two that rotate fast, the short period non-oscillators, I also applied rotational broadening because they're rotating synchronously and the profiles were very different. So, I mean, models aren't perfect.
One last thing. So at the beginning you showed 19 spectra and said we're going to look at 8.
19 stars, you mean?
Sorry, 19 light curves,
Yeah.
and said we're going to look at 8. And then at the end, you were talking a lot about how with only 5 or 6 points, it was really hard to tell what the trends were. So why didn't you look at the other 9 stars or 11 stars?
Sure. So for this study, I focused on a subset that was representative of all of them. We plan to look at more in the future. It takes a lot of time to do one. No, I mean, so the sample that I selected was intentionally to basically span the physical parameter set of all the different types of stars. And this is kind of an in-depth first look at this subset. And there's a paper Patrick's leading right now that's going to look at the scaling relation laws for the full set of the 19, well, the ones that oscillate at least. So in the pipeline.
We have time for one more question.
I have like 3 of them. Which one did I pick?
The next one.
Well, let's go to the one that asks what's the point. So the mass and radius are overestimated, and other than trying to make agreements between the scaling laws, what other implications does this have? Why is it important? And what does it mean for the rest of astronomy?
Sure, so it's important because I think we'd like to use asteroseismology on a larger scale with both Kepler 2 continuing getting more data, going back through the Kepler data set and being like asteroseismology for everything, and future missions like TESS and things like that that are going to get good time cadence observations. Asteroseismology is a technique that's not going anywhere anytime soon, and we want to be able to use it to measure stellar properties quickly and reliably. And so these stars are kind of a good way to say, well, is it reliable? Because we know it's quick. Does that answer your question?
Well, I mean, if they're wrong, what does that imply for other parts of astronomy? Like,
everything's wrong. What do you?
just theorize. What does it mean in the greater context of astronomy? Your thesis.
Well, I mean, it means that asteroseismology is a very powerful technique, but we need to be careful with it, right? So if we're going to be using sets of stars that are selected astroseismically, then we need to be aware that we're missing some stars that aren't going to oscillate, and we need to be aware that if we're just blindly applying the scaling relations and assuming that it's the word of God, that it might be off in some cases. I mean, by having a detailed look at these stars, we have a set of some of the really best studied stars from 2 different perspectives that allow us to kind of come back and have a reality check for these larger surveys that we're going to be doing in the future.
Well, let's thank Meredith.
Do you want to say bye to your drawing fans?
Meredith, take your time. We have to
Bye.
do some paperwork.